Good morning. It's 11 o'clock and time for yet another Chai and Why. This is our fifth Sunday Chai and Why for those rare months in a year where we have a fifth Sunday. Normally, we'd be at Alexandra School, but unfortunately, given the current situation, we are still doing online sessions. Doing Chai and Why online has been quite an experience, and I must thank all of you who've joined in and are listening to us for your patience, because it's really very difficult for us to do something which is meant to be an interactive program in this format where we really cannot see anybody in the audience. And I'm happy to say that we have one of our people who the audience actually really loves at Chai and Why. She's doing this for the third time. And it's a pleasure to welcome Dr. Aaloka Kanhere. Aaloka works in the area of mathematics education. So after her PhD in mathematics from the Institute of Mathematical Sciences, she focused on mathematics education, spent several years with Ekalavya, and then joined the Homi Bhabha Center for Research for Science Education, where her research is on various aspects of mathematics education. But she's also taken a lead role in something called Vigyan Pratibha. So also if you'd like to see stuff for maths education, look at Vigyan Pratibha. It's a wonderful resource from the HBCSE. And today, Aaloka is going to actually take us through a journey in connecting geometry with some other fun stuff. And normally, Aaloka doesn't just do mathematics, she tells us stories. So I'm sure she has some interesting stories today as well. So with that, we'll get started. But before that, given that this is going to be something where audience, you have to help us and work with us and do some homework literally, because you're at home now. We need your help. So if you're watching us on YouTube, please remember to try and type in your comments in the YouTube chat. If you're on Facebook, put it in the comments in Facebook. So we have a few of us who are monitoring the YouTube and Facebook streams. And those of you who are on Zoom, you can also put it in the chat on Zoom, or if you're ready to answer, you can raise your hand virtually, and I'll come and ask you if you'd like to say what the answer is. So don't worry, this is not difficult stuff. We all know how to count, I think, 1, 2, 3, 4. She's not going to ask us to count very much. I don't think she's asking us a very difficult counting. So with that, it's all yours, Aaloka. And audience, do let us know. Please put in whatever you can in the chats, because that's how we can get back. If you can't hear us, if something is wrong, if whatever it is, just put comments in the chat. Okay, so let's enjoy this session. Over to you, Aaloka.
Thanks, Arnab. Hello, everybody, and so I'm usually a person who tell stories, as Arnab says, but stories are no fun when you don't have faces who tell you that they like the story, they hate the story. But I'm going to try things. So let me first say that so when I'm saying counting areas, we are not going to actually count areas. What we are going to do is we are going to count and find areas. So we are just going to count numbers and actually get areas. So that's the thing. But before I start, I have to start with a story. So I'll start with the story. So there's a king, Bahubali, and Bahubali had a very big kingdom, and but he had basically two loves of his life. One of them was his herd of elephants. He really loved his elephants, and the other one was his big coconut garden. So in his coconut garden, so he liked elephants and coconut garden so much that he actually designed his coconut garden something like this, so that when he sees from his palace, he actually sees the coconut garden like this. So it's combining two of his loves. So he was actually very happy about the coconut garden, but what he didn't realize was that these elephants used to come and basically trample over the coconut trees and basically like spoil the garden and its beauty. So now the king was conflicted, and what he said was, okay, let me just put a fence around the garden so that the elephants can't come in my elephant garden. The problem was that he did not want to be too unfair to the elephants, and he did not want the area to be so small for them to move around that he doesn't understand what is happening. So then so now what we are going to do is we are going to help King Bahubali find the area of this garden where the elephants are not allowed. Okay, so we are just basically going to count and help King Bahubali. I suggest that you all of you sit with a pen and a paper, because there will be some writing to do, some no calculations, but some writing to do. So please just sit with a pen and paper. I'm just giving you about a couple of seconds before I move on. So okay, so let's start. Okay, so we'll start this process of trying to find areas by counting. So can you see you can see the grid here. The grid here is like this. If you see that these two dots and these two dots have the same distance between them, let's call it 1 unit, right? So if we call it 1 unit, then this particular square has the area of 1 square unit, because it's a square, so it's 1 square unit, right? So that is one thing that we will remember, that this particular square is 1 square unit. Okay, so let's move on, and we will. Can you see these shapes? So you have 5 shapes here: 1, 2, 3, 4, and 5. And what we are going to do is we are going to find different ways of solving of finding area of these figures. So let's start with 1. So can you take some time out and see what is the area of 1? So you can just type it in your thing saying what is the area of 1. You don't have to write square units. You can just write the area of 1. I'm going to give you a couple of minutes because this is a fairly simple one. I will also go through with you about this one. So once you have got it, so you clearly have 1, 2, 3, and 4 squares, and then this is a triangle. But if you see, if I make it into a rectangle, then it is 2, and it's half of that. So that's again 1. So it's 1, 2, 3, 4, 5, right? 5. Am I correct? Yeah, I mean, you please let me know, one of us know that I'm not correct. So similarly, please go to the second one now and find the area of the second one. Now you have learned the technique of completing a rectangle and then coming to the triangle. So I guess you would have got it. I'm not giving out the answers right now because some people might take some time more. So I'll just come to it at the end. Anna, you're saying something?
Yes. So I'm just saying that those who are watching it, currently we are trying to solve the area of this figure 2. And a big hint that Aaloka has given is to try and complete a rectangle and then see if we can find an easy way of finding the area of the triangle. And the best thing to do is to put a chat window saying that I think the area is figure 2 area is so much. Okay. So I think that's all I was going to say. Please put your thing in the chat and we move from there.
Yeah. So, so I guess you would have got the second one. So I'll move to the third one. Third one is fairly simple if you just count the squares. So please do that. Okay. So now the fourth one. So this is the fourth, which is the area which you have to find out. Again, I'm saying that the tricky parts can be this particular tricky part can be again done by completing the rectangle. If I'm drawing the rectangle with my mouse, I hope it's clear. So yeah. So I hope that the fourth one is also done, and let's go to the fifth one. Now, fifth one is. Let me know if there's a problem, but otherwise it's again the same thing. You have right angle triangles and you make them into rectangles and you get an area out of it. You just count the squares basically, right? We're just counting squares. So fine. So I hope you have got your areas, and I'm going to show you the areas now, and we will see whether they're correct. Yeah. So these are the areas that I got. If there's any one particular one that you want me to discuss, please let me know in the chat.
So Aaloka, let's see what answers we've got. Let's just check some answers.
Yeah.
So
yeah.
1 is 5. 2 is 6.
Yeah. Right.
3 is 13.
Correct.
Somebody says 4 is 8 and 5 is 17.
Yeah, so there is a, let's go back to the fourth and the fifth and then see why my answers and your answers.
Okay, why don't we go start from number one? Let's start from the
Ma'am,
simple one.
how did the first one came 5? It should come 4, na?
So why don't we go from number
we'll do
one?
it again. Yeah, I'll do it. Yeah. So number one, if you see, you have, this is 1, this is 2, this is 3, and this is 4. So right now we have 4 squares. So straight away 4 square units, we are done. Now let's look at this triangle, and we don't know how to find out this triangle because one is, there's no square. But what we can do is try to make a rectangle out of it, right? So when we make a rectangle, we see that the rectangle has to be 2 now because it's made up of 2 squares. And this triangle is half of that rectangle. So it's 1, right? So this is 1, 2, 3, 4, and 5. That's why it's 5 square units. Is that clearer now? Okay. Next, let's go to the next one. Again, I said this is a right angle triangle. So I try to make a square out of it. And when I try to make a rectangle out of it. And when I try to make a rectangle, I will see that the rectangle has 12 squares. 1, 2, 3, 4, and then such 3 rows. So there are 12.
How did you make that triangle as a rectangle?
I just completed the rectangle like this here. See, can you see my mouse? So I just used this rectangle and tilted it, used a copy of it, tilted it and made it into a rectangle. That's possible, right? Yeah. So that's why you got a 6 here. This is fairly simple because you're just counting the squares. So when I count the squares, I'll get 13 of these. So this is not a problem. So now the fourth one. So fourth one, let's see. So let's first try to get the squares and put them in place. So we have 1, 2, 3, 4, 5. 5 squares. We are done. Then this particular thing is what we had seen here, right? So this is, I make a rectangle and then this turns out to be 2. Hence the triangle becomes 1. Similarly, if I go to this one and I make a rectangle, I'll say 1, 2, and 3 boxes. But it is half of 3, which is 1.5. So I have a 1.5 here and a 1 here. So that's 2.5. And then 1, 2, 3, 4, and 5. 5 here, that's 7.5. So that's how I got the 7.5. I hope it's clear now. I'm going to give you a couple of minutes to get the fifth one, though you know the answer, but try to see whether you can get the 16.5 now with the fifth one. Then I will actually again go piece by piece and calculate them. Yeah. So like, are people convinced that it is 16.5 now by the same calculation that I did? So you can basically just look at triangles and make them into make them right angle triangles and then make a square or a rectangle out of it. And then you get, so let's look at all the small parts, the big parts you would have got. So this is again 1 and this is 1, 2, 3, 4. So 2. So this is 3. And then there is a squares here. And the half is actually interestingly coming from this small triangle here, which is half of 1, hence half, right? So you get a 16.5 that way. Is this okay now?
Yeah. Aaloka, can you annotate your PDF with a marker rather than just your mouse? Does your software allow you to annotate with a colored marker or something?
No.
Or you've not tried this?
No, I haven't tried it.
Okay, don't worry about that.
Yeah. Okay. So hopefully this at least the mouse is slightly clearer. I'm maybe making big, so I'll try to make big circles. Fine. So this is the area of the first exercise we did. So so now we have got a hang of finding areas on the grid paper. So let's try another example and see whether when things like now one gets a bit more smoothly about it. Okay. So this is a bit, some of them are a bit more complicated, but it's again, remember, make rectangle triangles and then make rectangles out of it. So fourth might be the only one which is a slightly more complicated, but we will come to it also. So I'm giving you time to do this. So the first one right now. So please do the first one. Yeah. So first one is basically you make this into two rectangles like this, and that is half of those two rectangles. Or you can just make a whole rectangle like this, and half of that would give you this triangle. So the rectangle would be 1, 2, 3, 4, 5, and 6. So there are 6 of them, and half of 6 is 3. So this particular thing is actually 3 square units. So let's go to the second one. Now, Arnab, the chats are coming in for the first one. Did they come, or am I going fast? Okay. So let's look at the second one. You have 1, 2, 3, and 4, and half of that makes it 2. Yeah. Okay. 1, 2, 3, 4, and 5, and half of that is 2.5.
Yeah, so people are giving us answers on.
Yeah. Okay. So so then the fifth one is the same thing. You make a big rectangle out of it, and then you have 1, 2, 3, 4, 5, and 6, and 7. You have 7, and then half of 7 is 3.5. This fourth is a bit more complicated, but what I'm going to suggest is that you draw it on a piece of paper, and actually I'm of course going to give you the area of it, but I'm not going to give you the idea to get it. At the end of this session, I think we will get an idea, even more clearer idea about it. But I'm going to give you the area, but not tell you how to calculate the area right now. Yeah. So this is what we got. The first one was 3 because we got a rectangle of 3 and a rectangle of 6, and then half of that. Second one was we got a rectangle of 4 and half of that. This was 11. Right. So yeah, this was, I did a mistake here, right? Yeah, it's 2.5. Sorry, it's a mistake here. Okay, fine. 1, 2, 3, 4, 5, 6, 7. So yeah, so this is 7. So are we fine here right now? Yeah. And this is 3.5. So this is 1.5, and I want you to think about why this is 1.5. Yeah. Okay. So I'm moving ahead, and so now what I want you to do is find the grid points. So all the points, the boundary of these shapes. So each of the things, you just count the boundaries. Yeah. I'm going to wait. So boundaries are fairly simple. I'm going to give it, write this down, but you can take your time. Hello?
Ma'am, I didn't understood fourth and fifth.
You're supposed to count the points. So you have a triangle here, right? And each of the triangle has these dots on the boundary. Can you see the dots on the boundary? Yeah. So you're supposed to count the dots. That's it. So like, for example, let's count one here. 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 of them on the boundary here. Is that okay now? Yeah.
Ma'am, I didn't understood fourth and fifth, not the first one.
You didn't understand what? No, fourth one. No, yeah, fourth one. I'm saying that you just take it easy for some time. At the end of it, we will get it. But I would also like you to think about how to find the area of this yourself. Instead of me giving you the idea for it, you just draw it right now on your piece of paper and see how you find the area for this one on the grid. And at the end of it, you will get an answer. You will get a solution for this. Yeah. I don't want to just give ready-made answers. This, you will get it. I mean, I'm very sure you will get it at the end of it. I will definitely get an idea also.
Aaloka, can you just give us the example of how you are counting these points on the boundary
Okay.
for another shape?
Yeah, so I'll just do it for this one only, the first one, which can be seen. So you have a 1 here. So you can see that the triangle is moved around the grid points like this, and there are some grid points which are on the line of the triangle, the boundary of the triangle. So you have 1, this point is on the boundary. This particular point is on the boundary. This is on the boundary. This is on the boundary. This is on the boundary. Similarly with this, this, and this. So you have 1, 2, 3, 4, 5, 6, 7, and 8 points on this boundary. Right? Is that okay now? Or do I repeat?
Yeah, I think that's good. That's good.
Yeah. Okay. So I'm going to give you some time to calculate these boundaries. Yeah. Fine. So now these are the boundary points that I hopefully each of you has got. Have you got these boundary points? So let's do it for the fourth one. 1, 2, 3, 4, and 5. So there are 5 boundary points here, right? So that's how this 5 is coming here. Similarly with 9. Okay. I'm going to give you now a couple of minutes to look at this table and see if you can see any relationship between A and B. So any relationship between, say, this 3 and 8, this 2 and 6, this 2.5 and 7, 1.5 and 5, and 3.5 and 9. And I'm going to wait for you to type it in the chat, the relationships that you get. And maybe Arnav can tell me what the chats are saying, because I'm not being able to see the chat somehow. I don't know why.
We are getting some things on the chat. I will just see what is coming in. Just give me a second. I am looking at okay, it's nothing on the. I need to just check the Facebook one as well. Just a second.
Ma'am, I am not able to count area in square units. I know.
This one, first one, can you see that I can make a rectangle out of this triangle, the first triangle?
Yes, miss.
Right? And this rectangle will be double of this triangle. Can you see that?
Yes, miss.
And can you find the rectangle in square units by just counting the squares?
1, 2, 3, 4, 5, and 6.
Right. So then what is the area of the triangle now?
6.
The rectangle is 6, but the triangle is half of the rectangle.
Yeah.
So what is half of rectangle? You got it now?
Yes, miss. 3.
3, right. So now you can do it, right, with each of them. Yeah. Yeah, now.
Okay, so we have the first few comments.
Yeah.
The first few comments. Let's see. On YouTube, there is someone who's saying that B is A plus 1 squared.
Okay.
And on Zoom, there is somebody who's saying B divided by 2 minus 1 is A.
Okay.
So we have 2 answers so far.
Yeah. So I would like to wait for a couple of minutes. Yeah.
Okay, there is one comment.
Yeah.
That people are not getting the boundary points concept. I think you should explain that these are the points that are on the line.
Yeah. So these are the boundary points. The number of grid points on the boundary is basically the points on the line that is drawing the triangle. So you have 1, 2, 3, 4, 5, 6, 7, and 8. in the first one, where you each of these points are on the line which is basically making the triangle, right? So the lines which is making the triangle, each of these points are on that line. We have to count those points. So in this case, I'm again counting. Let me.
I think start with number 2 or 3. They are much easier than 1.
Yeah, I'm doing that only. So let me see. I'm going to. No. So this is 1, 2, 3, 4, 5, and 6. So I draw this line. This lines is making, these 3 lines are making the triangle, and all the 3 lines are passing through some points which will be on the boundary. So I'll count again. I'll count the third one now. So I have 1, 2, 3, 4, 5, 6, and 7. So that's the 7 on the boundary. Is this okay now?
So maybe you can add that the diagonal line does not go through any of the points except the ones at the 2 corners, and those you've already counted in the sort of vertical and horizontal.
Right now the line is not passing through any of them, but that need not be the
in this particular shape.
The line passes, but the line can pass through like in this case it is in some sense passing through the lines diagonally, right? In the fourth one, it's not a straight line.
Only for the third one.
Yeah,
and
only
the second
third one. Yeah, third one, there is this line is not, this point is not on the line, it's away. Maybe the thickness is making us feel that they're touching, but actually they're not. Here they're clearly very different, but I'll still say that this is not on the line. Yeah. So those of you who have come up with like somebody who came up with b is equal to a plus 1 the whole square, what I would suggest is just look at each of them and see whether the pattern that you have got, b is equal to a plus 1 the whole squared, is actually correct or not. Is it holding for each of these? Because it should hold for each of them, no? So for example, if a is 3, then a plus 1 is 4, 4 squared is 16, while your bound b is 8. So doesn't look it's working, right? Is it square or it's 2? Arnab, is it a plus 1 into 2? Is that the person saying that? Okay, so I'm going to move ahead. Arnab, you're saying something?
Yes, b is a plus 1 into 2.
Right. So
okay, I'm sorry, Swarnava and all. I'm looking at a very small screen. I'm looking at this on multiple small screens, and I'm really sorry. I looked at that. I thought it was squared, but no, it's a plus 1 bracket into 2.
Right.
And
fine.
that is what many people have said.
Okay, so great. So there are 2 patterns that you gave me. One was b is equal to a plus 1 into 2, and b by 2 minus 1 is equal to a, and they are both correct, right? This is the relationship that is coming through for both. So I have opened the bracket and I've written it as b is equal to 2a plus 2, which is the same as a plus 1 into 2, right? Double of area plus 2. That is 3 into 2 plus 6 plus 3 into 2 is 6 plus 2 is 8. Right. Now, because we are into finding areas, we will basically only concentrate on this right now, right? But both of them are equivalent. I mean, that is clear to all of you, right? That actually they are the same. I'm just taking the b on one side, 2 on one side. So, yeah. So I'm going to look at this one. And now you remember the first part where we were having trouble finding the area. We'll come back there and see whether this b by 2 works for it also. And then if it works, then we are done, right? I mean, nothing like it. We just count the points on the boundary and we get the area. That's cool. So, okay. So let's see. So now you have got the idea of finding boundary points. So please, I mean, I'm going to give you the boundary points because I mean, people were having, I'm going to wait for a couple of seconds for people to tell me the area or the boundary points for first figure. Figure 1, this figure, I want you to tell me the boundary points for this. If that once that is done, then I will move ahead and give boundary points for each of them. You don't need to do that exercise of counting again. So just give me for one, and then I'll move ahead. So
Okay, a lot of people are saying 12.
12, right? Okay. So these are the boundary points. If you don't trust me, you can go and check out one of few of them more. But that's right. I mean, I've double calculated. So, okay. So now what we have to see is that whether A is equal to B by 2 minus 1 works for this, right? Because we know the area, we know the boundary points. So let's see whether A is equal to B by 2 minus 1 works for each of these 5 things. So is it working for the 5 things? For these 5 figures, is A and B, the relationship is A is equal to B by 2 minus 1. Is this relationship holding? Clearly no, right? Because no, I don't know. Maybe yes. So here the boundary is 8. So 8 by 2 is 4 minus 1 is 3, while we get a 6 here. So no, clearly it's not working, right? But is it working for some? Are there some numbers where A is equal to B by 2 minus 1 is working? Are there some figures where this relationship still holds? Can you just type those number of figures? Like, say if it works for, we saw that it's not working for 2, but it's clearly working for 1. So you can type, say, 1 and some other number, or only 1, or whatever. So can you type those and see? Yeah. So
There is a comment. There is a comment says it seems to work when there are no grid points inside the area.
Ah, okay. So
Somebody says it.
Yeah, so I'm coming to that. Yeah. So 1, 3, and 5 is where it's not work. Sorry, 2, 3, and 5 is where it's not working, while 1, 4, and 1 and 4 is where it's working, right? As somebody rightfully said, so I was going to ask you the next question was, what is there in 1 and 4 which is not there in 2, 3, and 5? Or what is there in 1, 3, and 5, 2, 3, and 5 which is not there in 1 and 4? So yes, interior points, right? The points which are inside the thing. Like in this case, there are 3 here. In this case, there are 4 here. In this case, there are some here, right? So if you have the points inside the shape, then A is equal to B by 2 minus 1 is not equal to, right? A is not equal to B by 2 minus 1, clearly. But we also know that interior points are seeming to be playing a role. Some role they're playing. We don't know what role yet. So why don't we go and actually now calculate the interior points of these? So for each of them, so for example, 1, we know it's 0. For 2, it is 3. Let me just clarify that this particular point is not in the boundary. It's an interior point. So there are 3 interior points in this second figure. There are 3 interior points. So I want you to calculate the count the interior points for each of these figures now. So first one is 0, second is 3, third is 4, fourth is again 0, and fifth is 8. Is this what you also got, each of you? Okay. Now try to find a relationship between A, B, and I, but keep in mind that B by 2 minus 1 is playing a role. That is not going anywhere, right? So now can we find a relationship between A, B, and I? I is the points in the interior, as one of you had said that the figures which do not have interior points, B by 2 minus 1 seems to work. So now that's why we are trying for interior points. So I want you to see if you can find a relationship between A, B, and I now. Remember B by 2 minus 1. Don't forget that. That has to be there. because that seems to working. So what is working? Why should we let it go, right? So yeah, what are have people got something?
People are commenting. We just give them 30 seconds more, and then
Yeah,
we'll see.
no problems. Yeah, all the time. Yeah, no problems at all.
So we'll get some more people check if they want to comment.
Yeah.
Okay, so the most common comment seems to be b by 2 minus 1 plus the I.
Okay.
And let's see what's happening on the Zoom chat. Again, it is b by 2 minus 1 plus I, or I plus b by 2 minus 1. Everybody's saying it's add I to your earlier b by 2 minus 1.
Right. So this, right? That is what everybody got. That A is equal to b by 2 plus I minus 1. Right? I just added the I to the b by 2 minus 1. And it's absolutely correct. It's actually not just correct. It's actually a very, very famous theorem called Pigs Theorem. And so this, I would like to talk a bit about Pigs. George Pick was his name, and he was born in 1859, and he published this about 40 years later. That, I mean, when he was 40 years old, he got the Pick's theorem. He has contributed in a lot of areas, but the interesting thing about Pick is that so he was born in a Jew family, and so when he retired, he went to Vienna, and then the fascist Nazis invaded Vienna, and he fled to Czechoslovakia, Prague, and then they caught him there, and then they actually put him in a concentration camp at the age of 80, where he died at 82. So very famous life, and yeah, so that's about Pick, George Pick, and this is Pick's theorem. And what we did today was actually discovered Pick's theorem on our own, right? So, but interestingly, so now what happens is actually Pick's theorem helps us that to solve Bahubali's problem, right? If actually Pick's theorem is true, then that Bahubali's problem can be solved, because all we have to do is count the coconut trees inside and the coconut trees outside. I'm just going to go back to the Bahubali thing. Yeah. So this was the Bahubali problem. And so now we have solved it, because all we have to do is calculate the points and we are done, right? But there is one problem. And the problem is that, yes, we found for 10 different shapes, and Pick told us that is true, but we haven't checked whether it's true, right? So let's try to see whether with small geometric things, can we come to some kind of a conclusion about why this Pick's theorem actually works, and whether does it really work, right? I mean, I told you, but one shouldn't have, you don't have to believe me just because I work in maths education, right? So let's see whether it works, right? What I would suggest is I will give you next, I mean, I already shared my email ID with you. It would be nice if you can draw some grid, some shapes on the grid, and even send me pictures of it, or send photographs of it. Tell me, give me comments about whether you could actually get the area of it, and then also draw really complicated things, and use this to do it. But first, we need to really see whether it works, and we'll try to do that. So what we
Aaloka, if I may interrupt you.
Yeah.
You know, in school we had always taught areas is something like length into breadth for a square, or half base into height for a triangle. And suddenly we've moved away from that to counting just points.
Yeah.
How do you get areas from counting? I mean, are you going to tell us about this later?
Yeah. So
I'm really amazed that you can just count the number of points and it gives you an area. Whereas I always thought for an area you have to multiply a length, and you have to multiply two lengths to get length squared, something centimeters squared.
True.
Right?
So yeah. So I think one thing is that you have these squares, right, which you're counting, right? So what you're looking at is you have a shape and how much squares can you cut and put in? That's actually the area. Area is not length into breadth. Area is how many squares can I put in a shape, right? So, so this, I mean, why this works, we will see why it works, why this particular thing works. But actually, every square, I mean, every area can actually be found by counting, because all you have to do is fit squares into it, right? And wherever you're not fitting squares, you cut and some parts of the square. So you put a half a square, you put 1/4 of a square, or whatever. I mean, ultimately, you're just filling the area. So area is actually just filling, like, what is the area of a shape is the what I need to fill the area of it, right? It's as the textbook says, it's area covered, or area occupied, space occupied. Space occupied is one word that is always said. So yes, that is why I think counting works, because here you're counting the square points, and what basically you're going to do is find a formula which will help you get the square points. That is why this works. Is that kind of answers your question, Arnab?
Yes.
Okay. Okay. So now what we are going to do is we are going to try to prove, or at least see, come to a come to I mean, come to convince ourselves that this is true, because we should not be convinced because Pick said. You should not be convinced because I said, right? We should be convinced because we see that there is mathematics in it, and mathematics is telling us that it's correct, or science is telling us that it's correct, right? So, okay, let's start. So what do we have to do? We have to prove that this particular, like a polygon like this, a complicated polygon like this, even there, a is equal to b by 2 minus 1 works, right? Okay, so how do we go about doing this? So so we have to prove. So let's have a checklist now. Okay, so checklist is that we are going to like actually go start putting tick marks and see where we have reached. So you have a is equal to b by 2 plus I minus 1 for is true for all polygons on the grid. That's what we have to prove, right? Okay, so we actually showed for 10. Okay, fine. So look at these polygons here, and they can actually divide it into triangles. Any polygon can be divided into triangles. I hope people are convinced with this, that any triangle, any polygons can be divided into triangles with this technique, where you take one vertex and then you join it with all the other vertices except for the two adjacent vertices, right? How many triangles will you get? So if I have a vertex of say 5, how many triangles will I get? If I have a pentagon, how many triangles will I get? There is a pentagon here actually. Yeah. 3 triangles, right? Because there will be 2 which will be taken off. So if I have n vertices, then I will get n triangles, but triangles it is. So I will definitely get triangles, right? So now, so instead of polygons, if I can prove for triangles, I am done, right? So if I prove that a is equal to b by 2 plus 1 minus 1, b by 2 plus I minus 1 is true for triangles, I'm done. But there is a problem, right? Here we are putting things together. We are actually gluing things. So we need to check, because when I glue things, I will have a common boundary. When I, like, these 2 triangles are put together, there is a common boundary here, right? I'm gluing them. I'm pasting them, like the way, and then that's why the dotted line, like in the origami thing, so you're pasting them. So we need to also check whether it works for pasting, which is basically saying that if I glue 2 polygons along the edge, then a is equal to b by 2 plus I minus 1 still works. Okay, so let's go for the triangles first and see what happens. Okay, so this is a triangle, and we have to prove it for this triangle. I mean, of any triangle like this, right? Or triangles like this. And now here is the thing that I told you about, the 4th problem there, that I will not give you the answer right now, but you will get it, is because this particular triangle is very similar to that triangle there, right? Okay, now what I'm going to do is, so any triangles like this can actually be surrounded by rectangles and right angle triangles, right? And rectangles, finding area is fairly simple. We can at least count the squares, right? We know how to count the squares. Right angle triangles, we learned the technique of making that into a rectangle and finding, right? So every triangle, any triangle, again, this is another thing I'm going to give you as a homework. Any triangle you take on the grid can be surrounded by right angle triangles and a rectangle, mostly 3 right angle triangles, but in some cases like this, 2 right angle triangles. So 2 right angle triangles and a rectangle are enough to actually surround this, right? It's a nicely composed now, it's like nicely included in the thing. So let's go back to our checklist. So now, so instead of this triangle here, if I prove Pigs for this, am I done? What do you say? So I don't, this is very complicated. I can't find Pigs theorem for this, but I can find for this and this and this. Then am I done? What do you say? What do you think? Will I be done if I cut this? Anna, do you want to say something?
Yeah, I'm just trying to think about what you said about the triangle. You're saying that any triangle will fit inside a rectangle.
Yeah.
Right. And
Yeah.
if I look at the part which is outside the triangle, it is composed of 2 or 3 right angle triangles.
Right.
Sometimes 2, but mostly
Sometimes
3.
mostly.
But any triangle can be thought of as fitting inside some rectangle.
Right.
And because I know how to calculate the areas of rectangles and of maybe of these right angle triangles, I can try and solve a simpler problem than the original problem of some funny shaped triangle somewhere.
Right. I think, yes, correct. Absolutely.
Is that what we're trying to do?
Yes. So what?
Yes.
See, we started with a very complicated polygon, and then we cut it into triangles and got a simple, slightly simpler figure than a complicated data made a polygon, right? And then we cut it. So, so these were like very complicated polygons, right? And then we cut them and got simpler shapes like triangles, right? And we said, okay, so if we can do triangles, we can do these polygons, and it seems that it will be easier to do for these triangles. So why not let's stick to the triangles. So that's why we decided, okay, if we do for triangles, we are done for the polygons, and it's easier for the triangles. Then why do it for the polygons at all? So that's why the triangles, right? Okay. Then we came to the triangle, and we say, okay, so this is a triangle, and if एक सिंपल प्रॉब्लम को और भी सिंपल कर सकते हैं तो क्यों नहीं करें, है ना? तो ट्रायंगल सिंपल है, लेकिन अगर मैं ट्रायंगल को ऐसे रेक्टेंगल्स और राइट एंगल ट्रायंगल्स के से सराउंड करती हूँ, if I surround it by rectangles and triangles, it becomes even bigger, a simpler, even more of a simpler problem. I mean, simpler problem. So that's why I'll get it. So I'm basically, what I'm doing is, I'm actually, to get a general polygon, I'm actually going to just find examples of small things, like specific things like right angle triangle and rectangles, and actually solve a much larger problem, right?
Okay, there's one question which says that you spoke about gluing. You have to be careful about the gluing of the edges. But if you're talking about areas, then why does the edge matter? Why does gluing the edge matter?
That's a good point, actually. But we are not just talking about areas. What we want to check out is if A is equal to B by 2 plus I minus 1, right? The boundary points, interior points. When you have a gluing, then what is happening is that the interior points are becoming your boundary points, right? For example, let's look at this. For example, look at these two. Now, in the whole rectangle, all these points on this are actually interior points of the rectangle, right? But they are boundary points of this triangle and this triangle. So now that complication is going to be there with your boundary points and interior points mixing, plus there's a -1. So just putting together, you're going to get a -2. So you have to adjust the -2 in some ways so that there's only a -1, right? Because we are not proving for areas. What we are checking out is whether this will work for all polygons. A is equal to B by 2 plus I minus 1, which all of us together agreed seems to be the answer, right? So what we are trying to find here is not area, but that's a good point. And I should have said it, that the reason the gluing is important here is basically because now your interior and your boundary points are going to mix, right? Am I clear now? Is this okay?
Yes, the person has written is got it. thanks for the explanation. So I think you're doing great.
Thanks a lot.
Okay, thanks, Ram. Thank you.
Yeah, thanks for stopping me also. That's so.
Yeah, this is the problem with this online format. But we'll get there. We'll get there.
Yeah, or maybe we don't have to, and we'll go back to old times. So yeah. So this is so this was our checklist. So you have that A is equal to B by 2 plus. We have to prove that A is equal to B by 2 plus I minus 1 is true for all triangles, and gluing of two triangles. But now what we have shown is that we don't need for all triangles. It's enough to show for right angle triangles, right? Which is a very, very specific case of triangles and much simpler life. But there's one problem. Now, because it's not just gluing, it's also removing. So in some sense, you also have an ungluing problem now. So you have to also unglue. So when you have to show that because ungluing has the same problem as the boundary and the interiors being mixed. So in ungluing, boundary becomes interior, and in gluing, interior becomes boundary, right? So, okay. So, but there's one more. And that thing is that we have to do for rectangles. All straight rectangles, not tilted, because tilted becomes complicated, but straight rectangles, we have to do it for straight rectangles. So these are the three things, right? So I'm going to surely run short of time, but I will do one simple counting exercise to show why this particular thing works with rectangles. So why is that in rectangles we can actually A is equal to B by 2 plus I always works, and that's why I don't have to actually each and individually count the squares. Yeah. So let's go back. Let's go to right for a rectangle now. So we are going to prove this for a straight rectangle. Okay. So look at these rectangles here. Yeah. Okay. Now I'm going to do a bit of a boring exercise. Is that you have to find the length and the breadth and the boundary and the interior points for all of these 5 rectangles, right? I'm going to give you a couple of minutes and then do the first one with all of you. So I'm just waiting for people to do it. Yeah. So the length. So remember that the number of boundary points on the length is 1 more than the length. So for example, this length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. But if you count the boundary points, there would be 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? It's this childhood puzzle that we used to have, that you have a 80 centimeter strip, and you have to make it cut it into making 1 centimeter each, and how many cuts will you give? So you have to give only 79 cuts for 80. It's the same thing, right? So the number of points in between. So fine. So hopefully people have got the hang of it. You don't need to get answers for each of them. It would be nice if you can finish at least one or two rectangles for the length, breadth, and the boundary points. It would be, I mean, we will do a counting ourselves, but still. Yeah. So I'm going to move ahead and complete the table for you. So these are the lengths and the breadths for the rectangles. I hope I have done it correctly. Yeah. So now let's calculate the boundaries, right? And I'll tell you why I'm counting the boundaries. So, okay, so let's count. So I have, as I said, I have 12 here and 12 here. So that's 1 more than 11. So 2 copies of 1 more than 11. And only 2 here because 2 are getting cancelled, already counted from the 3. So from the 4 boundary points. So 2 from here and 2 from here. That's 1 less than the 3. So 1 more than 11, 2 copies of that, and 1 less than 3, 2 copies of that. Right? Okay. Now what happens to the interior points? Interior points is interior points is that if you see, I get a rectangle. So the interior points is also again a smaller rectangle whose breadth is 2 less, right? So there are 2 points. So the length is 2, but now you're counting points. So there are 2 points. So there are 3. The length is 3, but there are 2 points here. And similarly, the length is 11, but there are 10 points here. So hopefully you people calculated and got these. Just excuse me. Yeah. Sorry. Yeah. So is this fine? Do I move ahead? Yeah. I'm going to give you a couple of minutes to get the structure till we actually go and find the structure. Yeah. बोलिए.
Ma'am, it should be 12 and 4 now.
For the first one.
For the first one.
The length.
Yeah.
Yes.
Just calculate the length again.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, ma'am.
12.3.
The dots are 12, right? But the length?
11. Length is 11.
So I put the length as 11, no?
6, 7, 8, 9, 10.
Yeah, right.
3, 4, 5, 6, 7, 8, 9, 10, 11. अच्छा हाँ हाँ.
So that's the
Okay, okay.
That's the वही में मतलब वो एक confusion होता है हमेशा कि
हाँ,
dot
हाँ.
को गिनना है या length को गिनना है.
हाँ हाँ.
आपको so we have to calculate length. So when I say length here, you have to calculate length. When I say boundary points, you have to calculate boundary points. So in the boundary points, you will calculate 12 on both the sides. That's correct.
Okay, ma'am.
Yeah. So maybe this is something you might worth emphasizing that between 2 points there is only one length. So between 3 points there is 2 lengths. So when we are calculating length and points, there will be a small difference.
And that is a confusion that will happen here. For example, even in the inside rectangle, for example, though you see the length to be 1, but because you're going to count dots, you're going to count 2 dots. So in outside you will see dots, but you will count length, and inside you can see length, but you can have to count dots, right? So you have you will count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? Or you can look at it as 2 and 10 such rows. So that's 20. Yeah. So right now you can also see whether the Pigs theorem is working for this, because now you have boundary points and interior points and the length and the breadth, and we know area is length into breadth, right? So we can actually check. So boundary points is 28, which is 14. So 14 plus 20 is 34, and 34 minus 1 is 33, and rectangle of length 11 and breadth 3 gives me 33. So seems to be working, but that's not a proof. I agree. So yeah, so I'm going to move ahead and going to calculate. So now we are not going to look at actual dots. Okay, we are not going to count 1, 2, 3, 4, 5, 6. We are actually going to get some idea about how to do the counting. So my length is now assumed to be L. Don't say it's 11, it's 12, it's 13, 15. It's L. Okay, and breadth is B. Okay. Now I have to count.
Aaloka, just a question.
Yeah.
Somebody's speaker is on. Maybe your own speaker is on somewhere. Feedback. Okay, so this stuff is there on the Vigyan Pratibha site in case people find it very fast, because we have only about 15 minutes more. It might be really difficult to understand everything, but people can always go back to the Vigyan Pratibha site and go through it slowly, right? You'll show the link.
I'll show the link. Yeah.
Okay.
I will do the link. Yeah. Okay, fine. So I'm going to go to this rectangle and okay. So now this is a very interesting thing. So let's count the boundaries together. Okay. So there are different ways of counting the boundaries. The way I count it is that, so if I have a length here, I will say ki, okay, so there are L plus 1 dots here and there are L plus 1 dots here. And then because there are actually B plus 1, but this one and this one are already calculated, I have tried to mark them separately. So with a little bit of red mark, but I don't know whether it's obvious. So this and this is already calculated. So you have only these, right? So which is B minus 1. So you have 2 B minus 1s here, and you have 2 L plus 1s here and here. So this is the answer. So, but interestingly, what is 2 into L plus B for a rectangle? So what is 2 into L plus B for a rectangle? Yeah, we are leaving formulas behind, I know, but still, I mean, we know them since our childhood. So it's perimeter, right? And it's a boundary. So it is about to come as perimeter, right? Because it's basically boundary, right? So this is the boundary. And okay, now we are going to calculate the interior points. So interior points, again, you have, so because these are here in this particular line here, there are L plus 1, but then this and this are not counted. So there will be L minus 1 of them. And how many of L minus 1s that we will have? So you will have B minus 1 rows of L minus 1, right? Because you have L plus 1s here and 2 are taken off. So L plus 1 minus 2 becomes L minus 1. Similarly, there are B plus 1s on this dot, and then you are removing 2 from the sides. So you get this, right? Right. So you have L minus 1 into B minus 1. This is your interior points. Okay. Now remember why are we doing this exercise? We are doing this exercise to see whether Pigs theorem, that is B by 2 plus I minus 1, something that you people got on your own, actually works for rectangles, right? So I'm going to just go to go fast and see. Okay, so this is, so my B we got as 2 length plus 2 breadth, and my I got as length LB minus L minus B plus 1, right? I'm just going to put them together. Okay? Why don't you people just put each of them together in this and see what happens? I'm going to wait for a minute and maybe then move ahead. So you have to just have to put your B in this and your I in this and see what happens. Yeah. So basically something like this you have to do. So I just want you to like open things, cancel things, and see what happens. I'm going to wait for a couple of minutes. This is the like the last bit. So
Ma'am, can you just explain once how you counted internal points LB minus 1 minus B plus 1?
yeah. So you have this thing. So there is L plus 1 dots here, right? Is that fine? The ones that you calculated as extra length, right? So you have if this is your breadth, then you have B plus 1 points here. But then when I come inside and look at this rectangle here, I will only have B minus 1 points in this particular row.
Length
right?
is 14 in this.
Ma'am, that's what I'm said. Let's not look at 14.
Okay.
Let's not look at 14. We look at try to like get out of the numbers and just look at it as length and breadth. And just listen to me, right? So this length, this particular length, if this length is L, then how many dots are there in this line?
1, 2, 3, 4, 5,
L
6.
plus 1, right? If you have 11, then you have 12 dots, right? Between two dots is one length. So if this length is L, then you will have L plus 1 dots, right? Similarly, if this is B, then you have B plus 1 dots.
Okay, yeah.
Right? So now, but this and this is taken off. So this one's here will be, inside will be B minus 1 dots.
Okay.
And there are how many such lines? L minus 1 lines.
Yeah.
That's why it's L minus 1 into B minus 1. That's the multiplication thing that we get with dots, no? Yeah? Okay. Okay, so we are back to this. So now I want you to do the cancellations and see where you got. What did you get? So okay. So I just opened up, I just canceled the 2's and I got a L plus B. And now you tell me, just type the final answer on the comment screens with all the cancellations, with all the plus and the minuses getting cancelled. Like, so you have a L and a minus L and a B and a minus B and a 1 and a minus 1. So what do you get? This, which is L into B, which is actually area, right? So just by counting, we could prove that for the Pigs theorem for rectangle works. Okay. I'm just going to jump a bit because we don't have enough time, and I just want to look at our checklist. And in our checklist now we have finished straight rectangles. I don't want to go into too much of calculations right now because we are really running short of time. And but let's look at this one thing. So you have this P and Q, two shapes, and I'm going to glue them. And this is what I mean by gluing, right? So when I glue them, I get an R. So I have a P and a Q and an R, and I want to check out whether if I calculate all the area of this, that is B by 2 plus I minus 1 for this, and B by 2 minus I plus I minus 1 for the Q, and if I can get this B by 2 plus I minus 1 for R, it should be same, right? That is what I need to do. And so all of this, I will show you, all of this is there on the Vigyan Pratibha website, and I will show you the link to it at the end of it. But what I will say, and I leave you with a hint. The hint is that these points on the boundary, the common points on the boundary, play a very, very important role. So this C, like this number of points on the boundary, if we call it C, say common points, they play a very important role in your counting. But you will find all of this on the Vigyan Pratibha website. So I'm just going to go ahead and do for right angle triangles. So again, right angle triangles, I have a right angle triangle, I have another one, I join them to make a rectangle. So again, gluing and ungluing will give me from a rectangle to a right angle triangle, right? Again, it's there. I hope to finish it, but I couldn't, so I'm really sorry. But we can definitely help Bahubali. So maybe what you can do is spend some time looking at this thing and see how much area the elephants are not allowed in right now. I'm really sorry for running short of time and rushing at the end. But you can look at this site called vigyanpratibha.in. There are a lot of maths and science hands-on activities, which is slightly out of school syllabus, but connecting to school, something like that, what we did today, where you have some proofs that you do, some counting that you do. So there is area, there are concepts that you know, and you join all of them together to actually build something completely new, something that we didn't know about. So please do check on vigyanpratibha.in, and this particular unit is called counting areas there also. And I again apologize. I think I'm still feeling very challenged with this medium, and not being able to see faces I'm not being able to pace myself. So I'm really sorry about it. Thank you. Yeah.
Oh, thanks a lot, Aaloka. I mean, this was to me. I'm still trying to, I know all this length into breadth, and if you have a triangle, it's some S into S minus A into S minus B. There will be all these formulas that you mug up. And here is such a simple way to relate the area to just counting points. And yes, I know mathematicians love to do proofs. They're not happy unless they prove something. But I hope at least people have come up with, they have today learned some new way of finding areas. Which I think is great fun. And let's see if there are questions. People might have questions to ask. So would anybody like to ask questions?
I'll have a one comment to make.
Yeah, sure.
I think one of the reasons why I wanted to do this particular, try to do this proof was also because this is actually one of those very important mathematics theorems which you never come across in school life, but actually the proof of it with some time is high school level proof. I mean, we actually did not use any techniques of mathematics beyond class 6 in the counting, right? maybe 8 with a little bit of algebra dropped in. But the idea is that I wanted to also figure out this technique of proving where you actually, to be able to prove something very big, you actually just come smaller and smaller and smaller and smaller and smaller, and you actually just do it for something small and show that it's enough for the larger one. So that was the idea of that was basically the idea of doing this proof. um, yeah, all of this is available. It's also available online. This particular proof is also available online. But yeah, cut the knot does a lot of Pigs theorem. Very, very, very interesting ideas. But yeah, this area thing. Yes, I think GeoBoard, which is basically a board like the grid that we did, actually is a very, very interesting place to start learning area from, because you actually start looking at area minus the formulas, because there are such weird shapes that you draw that, see, length into breadth is only for absolutely clinical figures. No, you have these nice triangles, nice rectangles, then you have like whatever trapeziums, but they're all clinical figures. They're very, very clean figures. But with very nasty figures, one has to get ideas about how to actually check out the space covered, which is something which we should be doing in school when we start off. And it would be nice if children are actually doing it on the grid and finding out areas of really terrible shapes. So yeah, does that answer your whatever, something that you were still talking about, Anna? You are muted, Anna.
Okay. Yeah, I had sort of lost my Zoom window in the middle of all this. Okay, so are there questions from people? And if not, I would like to start with one question. So far, all the polygons you drew had straight lines. What if the polygons had curved lines? Would it still work?
Yeah, so Pigs doesn't apply there. No, Pigs doesn't apply there. It only applies to polygons without holes. So, for example, even if Bahubali had a lake in between the garden, your pig wouldn't work there. But there are some interesting things that people have done about finding Pigs theorem, generalizing Pigs theorem for holes. But if Bahubali had a lake in between his garden, then pig won't work there either. So yeah, that's why I stuck to polygons. So it's only grid polygons that it works on.
Okay, let me just check if there are questions on YouTube. Okay, YouTube audience, if you have questions, please type them in the chat. Facebook also, if you have questions, please put them in the comments. Okay. Doesn't look like there are any questions coming in.
Okay.
So in which case, I guess. Yeah. Do you need to? Do you want to say anything?
No, I think I just reiterate. Like I would really like you to go on and draw it on the grid. These really like complicated shapes and see. And it would be nice if you can post some pictures on the website or mail it to me or something. I don't know whether audience can post it on the Chai and Wai Facebook page, but it would be nice if like one could see these things to happen.
Yeah, you said you would explain that number, figure 4.
Yeah, so actually that is the rectangle thing that we did. No, that actually solves it. But I can go back and do it. So I was just saying that
there is one question from Facebook, of course, which is: does deciding which is interior or boundary point get tricky at times?
Yeah,
for example, in cricket, it can matter whether you're in or out depending on which side of the line you are. So.
Yeah, it will definitely matter a lot, and it is very tricky. And you saw it in some of my shapes where if the line thickness was a bit more, there was a problem. So yeah, one has to be a bit more careful about drawing our lines and having them really thin. Then it's not that tricky. But yeah, it can be tricky, and one has to try to figure it out. I mean, I think using a scale sometimes helps, because then you are not going in between the things. So yeah. So I had said I'll explain the fourth one. So can you see the figure in front of you, the second figure of that of any of these triangles actually? So what happens is, when you have a weird figure, you can surround weird triangle, you can surround it by right angle triangles and triangles and a rectangle, right? And we get it, and we get the So similarly, am I going back or sorry, I'm just yeah, you're talking about this fourth one, right?
Yes.
Yeah. So this fourth one, for example, now what we can do is, what the technique that we learned is that we surround it by a rectangle like this, and then we have right angle triangles will be half of rectangles, and a right angle triangle here, which is a half of a rectangle, and then you can find the area. Is that okay now? So you have a let's look at this. So you have a right angle triangle here, which is 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3. So 3 and 1, 2, 3. So you have a 3 by 3 rectangle and half of that, right? So that's 4.5. And then you have 1, 2, 3, 4, and 3 and 2. So that is 6. 6 is 3. So this is 3 and 4 and 7.5, right? And then you have a big rectangle, and you subtract all this from that, and you will get the fourth. Is this okay, or I should just do it again on the whiteboard? Is this okay, what I explained?
If you have a whiteboard, it might actually be very easy.
Oh, no, there's a whiteboard on Zoom, right?
Yes. See if we can.
Okay, I can just type, just 1 minute. I think there is a whiteboard on.
Yeah, I don't.
We have a couple of
enabled.
minutes. We have a couple of minutes, no?
Sure.
Sure. Yeah. So. Just give me a couple of minutes. I'm trying to just. Yeah. So I'm going to share screen.
Aaloka, there's a request to share the PPT. Can we share your PPT?
Of course.
Yeah.
No
okay,
problems. Yeah. I can also make a simpler PPT, because this is taking this is basically with the pauses. So if you want, I can send you a simpler PPT also, which is
okay.
So
yeah,
can
do
people
send us
see
something.
my
We will
screen
upload.
now?
Yes.
Yeah. Can people see my screen now? Yeah. Okay. So now, if you see, look at this triangle here, and it's a fairly complicated triangle to find from just counting the squares on this. But what I will do is I've surrounded it by a square, right, with right angle triangles. Now look at this particular right angle triangle here. This particular right angle triangle here with the blue line on the top. If it's a half of a 6 rectangle, 1, 2, 3, 4, 5, 6. So this is 3, right? So this is 3, right? Then look at this small one, this one small on the top here. I will have, it's 1, 2, 1, 3. So it's half of 3. So it's 1.5. Right? Similarly, if you look at this, it's 1 and 2. So it's half of 2. So it's 1. Right? Okay. So I have a 3 and a 1.5 and a 1 here. And then I have the square, which is 9. Right? So now what can I say about the area of this blue rectangle? What will it be? I hope the audience is the audience saying something about the area of the blue triangle?
I'll just check. Nothing as yet, but go ahead.
So I'm just going to remove the grid for some time so that.
Okay, the audience said 3.5.
Right. Right. Exactly. It's 3.5 because 3, 1.5, and 1 to get a plus with this blue triangle gives me a 9, right? So the blue triangle has to be 9 minus each of these, which is 3.5. So the same way we can do that fourth one. Is this okay now? Is this clearer?
Yes. I think this makes the method clear.
Yeah. So
okay. One question.
Yeah.
Is there a modification of this to calculate volume?
Oh, actually, it was a very interesting question. It has been proved that it's not possible. So some mathematician has actually proved that Pigs cannot be extended to three dimensions. Thank you for asking this question. It was it's nice to be able to so yeah, Pigs cannot be extended to 3 dimensions. Yeah, it has been proved actually. But it would be nice to actually see Pigs with holes. That is something that have been extensions. There have been extensions to that Pigs theorem that way. So I understand. I hope people understand when I say Pigs with hole. What I mean is a polygon of this size, polygon of this type. So something which has a hole in between. So like this is not counted now. So something like that. That is, people have extended polygon Pigs for this. So a polygon with a hole, but not 3 dimensions. I mean, it's not possible for 3 dimensions. That's what has been proved. Yeah.
Okay. So on that note, let us thank Aaloka for a wonderful session, taking us through all these little fun stuff in geometry where we actually counted points and figured out how to count areas. Remember, you can watch this on vigyanpratibha.in. It's called Counting Areas. That's the module. And we will be back again first Sunday of September. We will still be online in September. We will still be online. So do check out our Facebook page and we will also announce the topics coming up. We will probably be doing some simple experiments on the first weekend of September and then move to other talks in the middle of September as well. Till then, stay safe and have fun. See you at Chai and Y later. Bye.
Yeah. Thank you. Thank you.